On the second day of class, we learned a new equation. V is equal to delta D over delta T. We learned that that was valid every time we have a constant velocity, which means a velocity that's not changing, and an average velocity. So a velocity that is changing, but we don't want to find the changing value of it. We want to deal with only the average value of it. We call this our group A equation. There's only one. So it's not even really a group because it's only one equation. But we're going to call it our group A equation. A couple of days ago, we learned about some new equations, 5 of them, in fact, that are valid whenever we have a situation involving acceleration, when the object is speeding up or the object is slowing down. There's 5 of them, starting with A is equal to delta V over delta T. We have D is equal to VIT plus 1/2 AT squared. We have D is equal to VFT minus 1/2 AT squared. So almost the same thing. Just watch for that, right? These are all on our data sheet, but if we're not careful, then we might mix these two equations up. We also have VF squared is equal to VI squared plus 2AD. And finally, we also have D is equal to VI plus VF over 2, all in brackets, times T. Be careful with this one as well. A tendency of people with this one is to say VF minus VI over 2 times T. You kind of just get in that habit of, delta V, VF minus VI. That's not what that is. It's VI plus VF over 2 times T. Now, these are what we call our group B equations. Our group B equations, remember, we use them anytime we have an acceleration, anytime the object is speeding up or slowing down. And that's what we've been focusing on for the last couple of days. That's what we'll continue to focus on today, is problems involving acceleration. We spent a little bit of time yesterday kind of off on a bit of a tangent rearranging equations, a little bit of algebra. I want to spend a little bit of time rearranging a couple of these equations here right now, just to refresh your memory on that. Let's take this equation. Okay, let's take this equation, D is equal to VFT minus 1/2 ET squared. And let's solve for A with that equation. D is equal to VFT minus 1/2 AT squared. I want to solve for A. What's the rule? We had 2 rules, right? Actually, we had 3 rules. Okay, what was the first rule? Yep.
Get rid of what's not attached.
Yeah, get rid of what's not attached. All right. By the way, before we get rid of what's not attached, before we start following the rules, we have to make sure that the variable it's solving for is on the top, right? It is on the top here, so we're good to go. We'll start following our rules. The first rule was get rid of what's not attached. All right, so what is not attached to this, Patrick? Good, VF and T. So we want to take the VF and T over to the other side, get rid of it. How do we do that? Yes. Some people will say we add it because they'll say like, oh, well, we're subtracting VFT here, right? No, we're not. We're not subtracting VFT. What's in front of the VFT? That's a positive, right? So we take it over by subtracting. It becomes D minus that entire term, VFT, equals negative 1/2 AT squared. Does that make sense? Still solving for A here, right? Still solving for the acceleration. Now, what's the next rule after we get rid of what's not attached? Yep. Yeah, get rid of what is attached. All right, what is attached to the A?
So we multiply by 1/2.
And what else?
Times squared.
Yeah, and times squared. It's actually negative 1/2 and times squared. Not just 1/2, but negative 1/2 and times squared. So how are we going to take those 2 terms over? We can take them over one at a time, or we can take them over together. If we want to take them over together, how are we going to do that? Yep. Yeah, we're multiplying A by negative 1/2 and by T squared. So let's divide by 1/2, or negative 1/2, and T squared. It becomes delta D minus VFT, the whole thing, right? Divide it by negative 1/2 T squared. And that equals A, and that's exactly what we're looking for. That looks a little bit ugly there. Divide it by negative 1/2 T squared. So what if it looks a little bit ugly? Okay, as long as we can sub our numbers into there, we're good there. Does that make sense? Okay, let's try one more, and then we'll take a look at the 2 questions we had for homework. Let's take a look this time at, let's look at the last one here. This last equation here, D is equal to VI plus VF over 2 times t. Let's solve for t there. d vi plus vf, remember not vf minus vi, vi plus vf. It's on your data sheet if you forget. Solving for t here. What's the first rule? Get rid of what's not attached. Second rule? Get rid of what is attached. What do we got here? Everything is inside brackets. If everything is inside brackets, that's one term, right? Is that one term attached or not? It is attached, right? It is attached because it's multiplied by t. So how are we going to get rid of that one term? Divide. Yeah, so let's take that over by dividing. Delta d, this is going to look odd as well. Divide it by vi plus vf over 2 in brackets, right? We're dividing that entire term. That entire term is multiplied by t, so we're taking that entire term over to the other side by dividing. We get d over vi plus vf over 2 equals delta t. Solving for delta t. Looks ugly, so what? Now, I would suggest when you're subbing numbers into your calculator for this, do the bottom first. Like vi plus vf equals, then divide it by 2 equals, and then say d over that number equals, and then get your number. Don't try to use fancy, brackets on your calculator, because half of you are going to end up making a mistake on that. Does that make sense? All right, we had 2 questions on page 50. Let's go over both of these questions, all right? The first one says a skier moving down a uniform slope at 3 meters per second. Acceleration is -4. We want to find the displacement after 5 seconds. Is this a group A question or a group B question? It's group B. It involves acceleration, right? As the skier goes down the slope at 3 meters per second, the skier accelerates down the hill at 4 meters per second squared, speeding up going down the hill. That's a group B problem, and if it's a group B problem, then we're going to use our group B equations. We're going to pick one of our group B equations. Let's write down some givens first, though. We'll say for this one, what? Something is 3.0 meters per second. What is that? Yeah, what is that, William? VI. Yeah, it's going to be VI, the initial velocity. Now, this is going down the slope. Everything is going down here, right? Do you want it to, usually we make down negative, right? Do you want to make down positive here? Can we do that? Sure we can. We can make it whatever we want, whatever's convenient for us. Probably should specify that, though. Down is positive, therefore VI is positive 3.0. How many people made it negative? So everybody else made it positive? How many people made it positive? Okay, that probably makes sense here, but just be careful if you have an up and a down in the same question, that's when it gets really important to distinguish between positive and negative, all right? Okay, so VI is 3.0 meters per second. What is this 4.0 meters per second squared? What's that one correspond to, Jacob? Yeah, that's going to be the acceleration, and that's going to be positive because it's accelerating downward. Okay, if we made up positive, then VI would be negative, and so would A be negative. But for convenience, we made down positive. We have a time here of 5.0 seconds, and we're looking for the displacement here. This is a Group B question. We established that. Which of these 5 Group B equations looks like it fits the best? And like we've said for the last couple of days now, if you aren't sure, pick one. You can't pick the wrong one. And now, I say that, if you pick from this list, you can't pick the wrong one, because there is no wrong one. If you pick V is equal to delta D over delta T, that's the wrong one. That's going to give you a wrong answer, because that's a Group A equation. This is a Group B problem. Which one does he use? The second one, D is equal to VIT. Okay, let's write that down, and let's see how it matches up here with our givens. VIT plus 1/2 AT squared. Do we have VI? Yeah, we do. T, yes. A, yes. T, yeah. So it looks like this is going to work for us. VI is 3.0. T is 5.0 plus 1/2 of 4 times 5.0. Don't forget that square. That's a fairly common mistake. You know, we get caught up in writing our numbers out, and then we forget to put the square on that. Or at the very least, we forget to put the square in when we put it into our calculator. Okay, let's figure this out. I'll haul out the calculator so we can do this Follow the steps together here. Let's do it one step at a time. 3 times 5. You could probably do that without a calculator, right? 3 times 5 is 15. Okay, that's the first term. And now let's say 0.5 times 4 times 5 squared. That's the second term, which is 50. Now, pretty sure you can do this in your head. Okay, but if you can't, you haul out your calculator and say 15 plus 50, and you end up getting 65 meters. Now, they say it's 65 meters down, right? Is that what we got? Yeah, we got positive 65, and we define down as positive. So that means we got 65 down. Good? Question number 2 says a motorcycle traveling at 110 kilometers per hour on a flat road applies the brakes at 0.80 meters per second squared for 1 minute. How far did the motorcycle travel during this time? In Physics 30, I'm teaching Physics 30 right now, and we do this, what I'm about to do, a lot in Physics 30. And we've already done it a lot because you can imagine they already have a year of physics behind them. So we're progressing quite a bit faster with them than we are with you guys. You guys are doing well. Okay, we're just not going quite as fast as we would in Physics 30 at this point. At this point in Physics 30, everybody in the class would look at this question and say, oh, I want to circle this and this. Why do you think they'd say that? Why do you think they'd say we want to circle kilometers per hour in minutes? Like, that would come to their mind right away. Rachel, why?
So that you know you're doing it differently.
Yeah. Like, when we're dealing with constant velocity, it doesn't really matter as long as we're consistent. But when we're dealing with acceleration, and this is a group B problem, an acceleration problem, right? Then I got to be in standard units, meters per second, seconds, and so on. So what I like to do, and what I always tell my Physics 30s to do, is circle or highlight, you know, with a pink highlighter or something, draw attention to things that are going to lead to a silly mistake. And that's one of the things that leads to a silly mistake, is forgetting to convert units. Now, there is one more thing here as well that you got to look a lot harder for that could lead me to a silly mistake. And the two things that I just circled are more obvious. What's that one other thing that could lead to a silly mistake but isn't nearly as obvious? Dammy? I'm sorry? Yeah, it's applying the brake, so therefore, good. If it's deceleration, then the 0.8 should be yes. I'm just going to write in negative there. Okay, good. That's perfect. Like, you make that positive, you will get the wrong answer. All right, this is a group B problem, so we'll write down our givens here, knowing that we're going to use one of these equations. Let's say, what is this 100 kilometers per hour? We know we got to convert that, but what does it mean here first? Is it V, is it VI, or is it VF? Is it what, Josh? VI? Did you say? Yep. It's the initial velocity. This is how fast the motorcycle is moving before the brakes are applied. 1 minute, what is that? We know we want to convert that, but what is that? That's the time. The acceleration is, Dammy just told me, is negative 0.80 meters per second squared. Not 0.8, but negative 0.8. And we're looking for how far traveled. We're looking for the displacement. Does it say that the motorcycle stops here? No, it doesn't, does it? Like, a lot of people in this question say, oh, I'll make VF equal to 0. Well, if it says the motorcycle comes to rest, then that would be fine, but it doesn't. So we can't assume that. Maybe it does, but we can't assume that. Let's convert this. 1 minute is how many seconds? How'd you do that? Time 60 seconds in a minute. So we times it by, multiply it by 60. 1 times 60 is 60 seconds. All right, how do we convert kilometers per hour to meters per second? Well, we got to convert two things, right? We just converted minutes to seconds. Good. Now we got to convert two things, kilometers to meters and hours to seconds. Good. Multiply by 1,000 to get meters, and then divide by 3,600 to get seconds. We got 100 1,000 meters over 3,600 seconds, which is, I think it's 27.77. What do you want to try here? Francis, which equation do you want to try there of our group B equations? Yeah. We'll try that. D is equal to VIT plus 1 FAT squared. Pretty sure that's the one that's going to work for us. But if it isn't, what's the worst that's going to happen? We get no answer. We're not going to get the wrong answer. We're going to know that it doesn't work. And we just try another one. Listen, to be successful in Physics 20 and Physics 30, especially Physics 30, but even Physics 20, the biggest thing I could say to you, besides, of course, showing up for class and working hard, like the biggest thing I could say to you is don't be afraid to make a mistake. Like, take a risk. Try stuff. Don't be afraid of making a mistake. Okay, it's like sports. When you're afraid of making a mistake, what happens? You make mistakes, right? Don't be afraid of trying an equation here. If it doesn't work out, it doesn't work out. Try something else. Don't be afraid of it. Okay, so VI is 27.778 times T is 60 plus 1/2 of A. Be careful here. It's negative 0.80 times T squared, 60 squared. Now watch really carefully on this one, because if you don't do this right, like if you make this tiny little mistake that a lot of people will make, then you're going to get the wrong answer here. We're going to say 27.7778 times 60. That gives me 1666. And then we say, now this is where you really got to watch carefully here, right, gentlemen? 0.5 times negative 0.8 times 60 squared gives me negative 1440. So we're adding not 1440, but we're adding negative 1440. Okay, obviously that's going to make a big difference. If we just added the positive number, we'd get about 3,000. If we had the negative number, they rounded to 2 digits. We'll talk later on in Physics 20 after the break about why we round a certain number of digits. Okay, for now, it doesn't really matter. To 2 digits, though, we get 2.3 times 10 to the 2 meters. Okay, what did it work out to be unrounded? 226. 226, okay? If you had 226 for now, that's absolutely fine, 226. All right? I want to do another example now. This one's on page 51. Man, they just keep on going, eh? This one says a speedboat slows down at a rate of 5 meters per second squared. So you're out there in the water on a boat going, I don't know how fast. Just we're slowing down, that's all we know here. The boat is slowing down at a rate of 5.0 meters per second squared. And it says it comes to a stop. The process took 15 seconds. What's the displacement of the boat? Is there anything here that we should circle in red or draw attention to? Yeah, it slows down at a rate of 5, which means that's going to be a negative value, yeah. Jacob? Okay, it comes to a stop. When I say we want to draw attention to things that can lead to a silly mistake, like negatives, like units, whatever, you can circle or underline really whatever you want that could lead you to a silly mistake. But I'll caution you against being too liberal with the red pen. You don't want to use it too much, because if you use it too much, then it doesn't draw attention to anything, right? Does that make sense? So for me, I probably wouldn't circle comes to a stop. That's important to recognize that it comes to a stop. And I might want to draw attention to it, but I'm going to save this, my red pen, for drawing attention to the things that really lead me to silly mistakes. If that's something that you always miss when you're writing down givens, then that's probably something that you should circle in red. Okay, but otherwise it might be something that you just maybe draw attention to, but a little bit less attention to. Or you just notice it in your givens. Okay, what do we got here? We got, this is group B, right? This is acceleration or deceleration, negative acceleration. We've got A is equal to negative 5.0 meters per second squared. We got a time of 15 seconds here. I didn't forget the negative because I circled or I drew attention to the deceleration by labeling it as negative in red. Anything else here? Jacob, anything else?
You have VF.
Yeah, VF is equal to 0, right? Comes to a stop. The final VF, V final, is 0 meters per second. And I'm just looking for the displacement here, I think. Yeah. We've got a list of 5 group B equations that we can try. Which one do you want to try here now? Ben? Okay, so this one here. Okay, let's give it a try. Ben, I think you're right. But if it's not the right one, oh well. VFT minus 1/2 AT squared. Oh, look at this. What's the value of VF? T is 15. What's 0 times 15? 0. Like I can just cross that off if I want, right? Because it's 0. That make sense? You know what? I'm gonna write in 0, the value of 0 there anyways. I don't have to, but I'm gonna write it in anyways. Minus 1/2 A is negative 5. T squared is 15 squared. Now watch this. Be careful about this. By the way, forward is positive, right? I didn't write that down, but sometimes when we go with just the standard way of positive and negative, sometimes we don't bother writing it down unless we do something different, like down is positive. What do we got here? Let's say 0.5. 0.5 times negative 5 times 15 squared. We get 0 minus negative 562.5. No, I think I'm good there. 0 take away negative 562.5. This term right here is a negative value, right? Negative 562, does that make sense?
Yeah.
But look, it's 0 minus negative something, right? Which becomes positive. So my answer is 562.5. I'll tell you what. Like you guys, you know, at your age may not appreciate this as much as I do, but the elegance of math. Like it doesn't mean we, you know, that math is fun or whatever. It's, for some people maybe it is, some people it's not. Whatever. But it's elegant in the sense that this equation combined with what I wrote down, including the negative 5 for the acceleration. I think it was Damien that told me it was negative 5, wasn't it? No? That was the last one? Who told me it was negative 5 for this one? Somebody told me it was negative 5. Whatever. If we didn't make that negative 5, we would have gotten an answer of negative 562, which would have made no sense. We're going forward, but our displacement is backwards. It would have made no sense. Mathematically, when you get the signs right, it's amazing how the answer works out to be the right sign, always. Okay? And if you forget the right sign or put the wrong sign in, then it's going to work out to be wrong. Math just works when you sub in the right things. We would technically now round this to Anybody remember the sig fig rules? Yeah, no, 2 decimal places. It would actually be, yeah, it would actually be 2 digits. This is 2 digits. This is 2 digits. So the final answer would technically be 5.6 times 10 to the 2 meters, 2 digits. Okay, if that made sense to you, great. If it didn't, don't worry about it till after the break. Then we'll focus on that, okay? If it made sense to you, by the way, if you know what I was talking about there, try it. When we do problems, try the significant figures. If it didn't, don't, like I say, don't worry about it. If that made no sense to you, don't worry about it. We'll talk to you about it after the break and get you on the right track with that. Yeah. Yeah. Okay, let's take a look at page 51 now. At your desks, watch out for the little things, right? Positive or negative, north or south, kilometers per hour, minutes, right? Watch out for those little things. You can't circle it because it's on a screen here, but you can like make a little note of it, star something, or as soon as you notice something, just right off to the side and circle it or something to draw attention to it, all right? All right, let's have a look up here. Question number 1 says, if the arresting device on an aircraft carrier stops a plane at 150 meters with an acceleration of -15, what is the time that it takes the plane to stop? This is a great question to illustrate a couple of things. Obviously, the physics, right? The acceleration, the equations, and so on. But it's also a great question to illustrate something that we will see often in physics 20, but especially in physics 30. And that is sometimes we read a question and we don't know exactly what the context is. Like a lot of you probably read this and said, an arresting device, whatever that is, right? My point for that is that, I'll explain to you in a second what that is, but my point is that it doesn't really matter what the arresting device is, right? You're not sure what that is. Don't get caught up in that. Don't lose sleep over that. Don't get scared and panic about not being able to do the question because you don't know what an arresting device is. The bottom line is, you know that the displacement is 150 meters in that question. You know that the acceleration is -15 meters per second squared, and you know that it comes to a stop. So you know that VF is equal to 0 meters per second. You just want to find the time. Listen, that's it, regardless of the context, that it's a resting device on an aircraft carrier or whatever. It doesn't really matter. Now, just so you know, an arresting device on an aircraft carrier is this steel cable that gets strung across the deck of the aircraft carrier. If this is the water, and our aircraft carrier is in the water, okay, and there's a plane that's coming to land on the aircraft carrier, man, it's got to land over a really short distance, right? The length of a ship, right? So you think, like, what would be wise of the pilot as that airplane is coming in to land? Well, man, you better fire the reverse thrusters and like slow down big time, right? As you're coming in to land on this aircraft carrier, so that you don't go over the edge, right? So that you don't land like this and it's like, oh no, holy cow, I'm going too fast, and then into the water like this, right? So as you're coming down, like, you better slow down, right? But that's ironically the exact opposite of what they do. So they want to stop in a really short distance. They don't slow down. They speed up. As the pilot's coming down, they speed up. Why do they speed up? Yep.
Because they have more control of the aircraft.
Yes, they'll have more control of the aircraft if they're going faster. Yes. In addition to that, what if they miss? Like, if you miss and you're going too slow, like, you're hooped, right? If you miss and you're going fast enough, what happens? Now he can pull up, or he or she can pull up and fly around and try again, right? But it creates a problem when you're firing your thrusters and going as fast as you can as you're coming down. You don't have enough space to land. So you can pull up if you need to, but you don't have enough space to land. And that's why they string this cable across the middle of the ship from one side to the other. Down off off of this airplane is a hook. So when this airplane touches down, it's going way too fast to stop on this aircraft carrier, but it's got this hook dangling from underneath it. And that hook, if the aircraft has landed in time, then the hook will grab the cable, and the cable will stop the plane. Now, if the hook doesn't grab the cable, then that means the pilot has landed a little too far up, and then what happens? Well, then the pilot takes off. He or she has touched down, and then the pilot takes off again. Does that make sense? Makes a run around again, circles around again, and tries again. So it avoids, hopefully, it's designed to avoid the aircraft crashing into the ocean. All right. Is this a Group B problem, Group A problem, or Group B problem? It's Group B, right? I mean, that's all that we're dealing with right now is Group B problems. But you do have to think that. You have to think into that question always, because come test day, on a unit test, which is still a ways off, but on unit test day, the questions are all going to be mixed, right? So you got to be thinking, is this Group A or is this Group B? This is Group B. What equation do you want to try here? Which one do you want to try? I know a lot of people were thinking the right thing because I was helping a lot of people with this and they were on the right track. Yeah, Patrick, which did you use? This one? Yeah. Yeah, that's exactly what I do as well. D is equal to VFT minus 1/2 AT squared. Now, a lot of people had trouble rearranging that. They had D, they had VF, they had A, looking for T, but it appeared in two places. So it's like, well, how do I do that? Well, if VF is not 0, that's a problem. It actually requires something called the quadratic equation that some of you have learned in Math 20. Some of you haven't if you're just taking Math 20 right now. But the good news is VF is 0. 0 times T is what? 0. So that makes the equation D is equal to negative 1/2 AT squared. Now it's much easier to solve for A here, right? Much easier. We have negative 1/2 and T squared attached to the A. How do I get rid of it? They're multiplied by A, so I'm going to divide, right? Some of you sub numbers in first. I don't like doing that, but it's okay to do that. I prefer to rearrange it first here. So I'm going to divide D by negative 1/2 T squared. Oh, sorry, 1/2 A then. Yeah, you're right. Thank you. Solving for T, so I'm going to divide it by 1/2. Negative, don't forget the negative there, divided by negative 1/2 A, right? Now how do we get rid of the square there? Square root it, so it becomes D over negative 1/2 A square root equals T. Now let's sub our numbers in. Now the question is way easier, right? The displacement of this is 150 meters divided by negative 1/2 of A, which is, what was A, neg 15? Oh, interesting here. Square root. You got something like this with top and bottom, especially when you got a square root thing, like do what's on the bottom first. Let's say negative 0.5, oops, negative 1/2 or negative 0.5 times negative 15 gives me 7.5, positive 7.5. That's the bottom number, 7.5, positive, because it's negative times a negative, right? Then we say 150 divided by 7.5. Whoops, that's not right. 150 divided by 7.5 is 20, and then we square root that, and we end up getting 4.47. They rounded to 4.5 seconds, 4.47, 4.5, whatever. Okay, we'll learn about the rounding stuff, let's say, after your little reading week break. Make sense? All right, let's take a look at the second question here now. Second question says, 1968 Corvette took 6.2 seconds to accelerate to 160 kilometers per hour. If it traveled 220 meters, find its acceleration. Red pen? Anything? Kilometers per hour. Some people were asking me as I was walking around and you guys were working on this, is VI 0? Well, you would think it's 0, right? But it doesn't say that. It doesn't say the initial velocity is 0, so we're not going to assume that. This is Group B problem. We're going to say the time is 6.2 seconds. We're going to say VF is 160 kilometers per hour, which is 160,000 meters over 3,600 seconds. What is that? Does anybody have that value in meters per second? What is it? 44.44. Thank you. Meters per second. My displacement is 220 meters. We want to find A here. I think we're going to use the same equation. D is equal to VFT minus 1/2 AT squared. And we're solving for A here, right? Get rid of what is it on the top? Yeah, like it's not on the bottom of an equation, so we don't have to worry about that. Let's follow the rules now. Get rid of what's not attached. What's not attached? VFT. So take it over by subtracting, right? It's not subtracted from 1/2 AT squared. There's a plus in front of it, so it's D minus VFT equals negative 1/2 AT squared. Don't forget that negative. Lots of people, when they do this, drop that negative. They forget to write it in. Now what? Solving for A still? What's attached to the A? Yeah, not 1/2 T squared, right? It's negative 1/2 T squared. So let's take that over by dividing. The whole thing, D minus VF times T over negative 1/2 T squared. And that looks ugly, but that's okay. D is 220 minus VF times T, 44.44 times, what is T? Oh, I didn't write that down as a given, did I? Oh, yeah, I did up here, yeah. Okay, so it's 6.2 seconds divided by negative 1/2 of 6.2 squared. How do you put this into your calculator? What should you put in first? No, not the top. Never put in the top first, unless you're really good with brackets. Let me let you in on a little secret, okay? If you think you're really good with brackets, you're probably not. You're probably not as good with brackets as you think. So do the bottom first. We say negative 0.5 times 6.2 squared. There's the bottom. Then let's say 220 minus, let's use some brackets now. I think we're okay with brackets to do this. Put this inside some brackets here. 44.444 times 6.2. There's the top. So the top divided by the bottom gives me 2.89, or they rounded to 2.9 meters per second squared. Good? You got the whole negatives and positives worked out and stuff? Guys, listen, here we are, what, just over, well, this is 2 weeks today, actually, into class, right? 2 weeks today into class. Like, we're going to come a long way in Physics 20. We've already come a long way. Look at what we're doing right now, and look at what you guys are doing pretty good at right now. Not perfect. We still have a little ways to go on this. That's okay. Okay, but look at where we are compared to where we were day one. Remember day one? Remember what I did day one? If I walk 5 meters this way, and then I walk 2 meters this way, what's my total distance that I walked? Like, look at where we're at just 2 weeks later. Okay, we're way smarter than we were 2 weeks ago, right? Way smarter than we were. And we're going to be way smarter than now come the end of the semester. All right, here's what I want you to do for the next few minutes and for homework here. I'm not going to do another example. I want you to do just page 52, questions 1 and 2.